Hello, I welcome you all. The problem reads, if a horizontal force of F is equal to 50 newtons and is applied perpendicular to the handle of the lever at E, determine the clamping force developed at G. The mean diameter and the lead of the single square threaded screw at C and D are 25 millimeters and 5 millimeters respectively. The coefficient of static friction is mu s equal to 0.3. This problem is coming from the Engineering Mechanics and Statics textbook, 13th edition by R.C. Hibbeler. So we have been asked to determine the clamping force at G at this point. Right, and we've been given the other properties. We've been given the mean diameter and the lead and the coefficient of static friction. Okay, so let's draw the free body diagram. So we expect some clamping force here. Okay, and we'll have also at G, that point there in the opposite direction, and let me call this F. All right, so to maintain equilibrium, okay, even when there's a hinge, okay, at a hinge you expect two reactions to just reduce unnecessary work. I know that at this point I'll expect a reaction force like this to maintain equilibrium, and then at this particular point here I expect a reaction like this. Okay, so let me call this as my LAY. I call this as my CY. Okay, and then at C I just expect the opposite. So I'll expect the force coming down like this that I'm calling CY, and then at D I expect the opposite, okay, because these are symmetrical. So the force on this other part here will be going like this in this part. So I expect this force here to be going up like this. Okay, this is my dy here. All right, you get it? Because as we apply a force at E, what is happening is this part, look at this part, as we apply a force at E, then we are going to cause a moment, okay, or the screw itself will begin to rotate, or okay, and as it rotates, this this nut at D will start going, this nut at D will be going down, right? Are you seeing that what is happening? The nut at D will be going down while the nut at C will be going up, okay? Okay. And when this happens, then it means we are going to be exerting a clamping force on this board. That is what is happening, right? Okay. So that is how we are clamping, okay? So a nut at D is going down, while the nut at C is going up, and therefore member GAC, is C, moving in this direction like this, okay? It's moving, it's rotating like this. The top part is rotating like this, while the bottom part is rotating like this, and hence exerting a clamping force on this board, okay? All right. So let me call this CY because this system is symmetrical, so I expect CY to have the same value as dy. So I'll call CY as my W, and since they will be the same, I also call dy as my W. So I've got two W's right now on the same threaded board, okay, and it has two nuts. And because we have two W's and these nuts are interacting with the threads, okay, at D, and the nut at C is interacting with the threads at C. And because there is friction between the threads and this particular nut, um, we expect friction, all right? And for us to overcome that friction, we need a certain magnitude of moment, okay? So we need to overcome friction both at D and then C, okay? So we need to take into account the effects of Cy, which is W, and Dy, which is W. So as we do our model, we will consider the two effects, right? Or we include them in the model at once. So let's draw our model quickly so that you see what I'm talking about. Okay, so we are saying the moment must overcome the moment must overcome the friction at the two at the two screws, if you'd want to call them two screws, at the two screws. I'll call it two screws stroke because there are also some nuts there. Okay, I'll call it this way. All right. So now let's draw our model. So if I was to draw my model, then I expect something like this. Sorry. Okay. All right. There we go. And then we have okay. There we go. This is not good enough. Sorry. Okay. There we go. So now here we expect the weight on these threads. The threads are two. Okay, where we have the two nuts and the threads. So we expect friction at those 2 points. Okay, so they are of the same magnitude, therefore I'm just to indicate them as 2W. Alright. Don't worry about the direction again to say they are in the opposite direction. We are not considering direction here for now. We are just looking at all the points that are going to have friction and that are going to be countered by the moment that we want to find. All right. In fact, the moment will help us find the force. All right. Okay. So what else? So we are trying to, this load here is like we are jacking up something. Okay. We are lifting up something. All right. So it's like we are pushing this against the incline. So we need to indicate our force in this direction like this. So we are applying this particular force, which is moment divided by R. Okay, this is the force on the screw, right? So it's moment divided by the radius of the screw. And then what else? As we do so, then we are going to expect friction, and friction of course will be in the opposite direction of motion. We expect F like this, and we expect our normal force like this. Okay, but instead of using this, we are going to use the resultant force R. Okay, so let's do some calculation of a few things here. We know that we've been told that let's draw our thread, one revolution thread. Okay, there we go. and this is our theta. So this one here is a 2 pi r, and this is our lead. Okay, and we are told that our lead is 5. Okay, and we are told that our diameter was equal to, let's check, diameter, the lead diameter was 25 and the lead was 5. So diameter was 25 millimeters. Okay, and therefore the R is half of that, which is just a 12.5 millimeters. All right, so tan theta is just equal to L divided by 2 pi r, which is equal to 5 divided by 2 by 2 by 12.5, so this just becomes 25 pi. Okay, which is just basically 1 over 5 pi, right? So let's do the calculation. What do we have? Okay, so tan of that, what do we get? We get theta is equal to 3.6426 degrees. All right, what else do we have? We have also been told that mu, the coefficient of static friction, mu is equal to 0.3, right? Therefore, tan phi is equal to mu. We know about this relationship, which is equal to 0.3, and therefore phi is going to be equal to, what is tan inverse of 0.3? This is a 16 point, rounding it off to 70 degrees. All right, let's fill in our information. So this one is our lead angle, and then we have this one here as our phi. Okay, and then we have also something else, which is here. Okay, this one there, this angle here is also equal to phi. Okay, therefore this whole angle here, we need to use it. This whole angle here is equal to phi plus theta. Okay, all right, so we have that information. We can now get, since our coordinate system is just x, y, like that, we need to rewrite r in terms of x like so, and r and y like so. So x is going to be equal to r. This is r sine phi plus theta, and this is r cos phi plus theta. Alright, so with this information, we can apply the equations of equilibrium. So say summation of forces in the y equal to 0. Okay, so what do we have? We have minus w plus r cos phi plus theta equal to 0. Okay, and then we have summation of forces in the x. Okay, what do we have? In the y we have two w's, right? So minus 2w, and then summation of forces in the x, we have this moment divided by r is also, this one is positive, and minus r sine phi plus theta equal to 0. Alright, so when we divide the two, then they'll give us a tan phi plus theta equal to m divided by r divided by 2w. So we know what tan is. Phi, we calculated what phi is 16.7. Then plus theta, it is 3.6426. Then m, what is our m? We've been told that 50 Newton is applied perpendicular to the handle at E. So just need to get this particular moment, because we know this particular relationship here. Let me go back. We know that m divided by r is just equal to fd divided by r, right? Okay, so this is going to be equal to 50 times 125 millimeters is just 0.125. Okay, 1.505. And then what do we have? Of course, this is divided by r. So we are saying divided by, the r can come down, and the r is equal to 0.0125. Okay, that's the r, and then times 2, then times w, right? Is that so? So let's work out this problem and make w subject to formula. There we go. So we have 50 by 0.125 divided by 0.0125 times 2, which is times 2. Okay, so, and then we have a 250, then we have a 250, okay, divided by tan 16.70 plus 3.6426. Okay, so we are getting W is equal to 674.2966. All right, 2966. What are the units? It's newtons, right? So this is newtons. Okay, so having found the W, so what we're just going to do is we're getting one arm, so we know that this is equal to W, which is 674.2966. Okay, so let's take moments about A. So just say summation of moments about point A. Okay, so if we did so, then we have f by point 2. Okay, f minus f by point 2 plus cy, which is just 674.2966 by point 2 equal to 0. Therefore, f, okay, is going to be equal to 674.30. So I think we have found the solution. We have found the solution. This is the clamping force. This is the clamping force that the boards are going to experience. Okay, as we apply a force of 50 newtons at E. Right. I hope this problem was this video was helpful. If it was, give me a thumbs up, continue subscribing and share my videos and channel. Bye bye, and see you in my next screen.